Hi, Scotties. Mrs. Underwood here. We're talking about lessons 8 and 9, which are a wrap up of this unit. Actually, it's half of the unit. So let's get started. Here is a description of a hiker's journey on a trail. A hiker walked briskly and steadily for about 30 minutes and then took a 10-minute break. Afterward, she jogged all the way to the end of the trail, which took about 20 minutes. There she took a 15-minute break and then started walking back leisurely, stopping twice to enjoy the scenery. Her return trip along the same trail took 105 minutes. So I already started kind of chopping this up into different things that I know are going to be represented on the graph. All right, so we can sketch a graph of the distance the hiker has traveled as a function of time based on this description. So remember, distance the hiker has traveled is the output. We're going to call it D. As a function of time, well, that's the input. We're going to call it T. So if my input is 30 minutes, that's my input. What's the distance, the total distance the hiker has hiked in 30 minutes? Well, we'll need to look at the graph for that. Let's go to 30. Here's 1 mile. This would have to be a half a mile. So maybe that's 0.6 of a mile. It's an estimate, a guesstimate. All right, so input, output. Input the time, output the distance the hiker has hiked. All right, next thing we're going to do is identify the intervals in which the distance increased or stayed constant. Okay, so notice this whole graph is sloping upward. So it is increasing. Her distance is increasing as time goes on, which makes sense, right? When you go for a walk, and if you're going to figure out how many miles you walked, the longer you walk, the more miles you'll get. So briskly and steadily for about 30 minutes. Well, that would be this piece here, briskly and steadily. Then she stops and takes a 10-minute break. Okay, so at this point, she's not increasing her distance, so it stays the same for 10 minutes. Then she jogs for 20 minutes. Then she's pooped, so she stops and takes another break. Her distance stays the same. And then she starts to walk back leisurely. All right, so she's walking back leisurely, and then she stops to enjoy the scenery. And then maybe she saw a tarantula. I was actually walking this morning and I saw a tarantula. It was kind of cool. All right, then she continues her walk after she saw the tarantula. Then she stops again. Maybe she sees a rattlesnake. I saw one of those this morning too. And then she finishes up her walk. And it takes 105 minutes for the return trip. Alrighty. Let's calculate how much the distance was increasing over the first 90 minutes. Okay, so I want to figure out what's my rate of change between 0 and 90, this interval right here. Well, at the end of 90 minutes, it looks like she's, I don't know, a little more than 2, maybe 2.1 miles. 2.1 miles, she started at 0 miles. And that's going to be over our minutes. She started at 0 minutes. So basically our rate of change is 2.1 miles every 90 minutes. But that's usually not the way we say rate of change, right? We always talk about like miles per hour, things like that. So we want to get the 90 minutes down to 1 minute. So we would want to divide in the top and the bottom by 90. And that would be 0.023 miles every 1 minute. Okay, let's talk about place value. This is the tenths place, hundredths place, thousandths place. So we could say that she goes 23 hundredths of a mile every minute. I should say that backwards, sorry. 23 thousandths of a mile every minute. or approximately 2/100ths of a mile every 1 minute. Oh no. Oh good, you could see that. Alrighty. Let's talk about some of those key features of graphs that we learned about. So this question is asking when the hiker had traveled the greatest distance. Well, that would be our maximum point on the graph. So let's find that point. Let's see. She will have traveled, this is the biggest distance. So this point right here is our maximum. Where would be our minimum? That would be the smallest distance, right? And she starts off at 0. So that would be our minimum. This one also has 2 other names. So this is where the line starts, right, on the y-axis. So we could call this also our vertical intercept. But the other thing about that is that this point is also where it crosses the x-axis. So that could be our x-intercept or our horizontal intercept. Uh-oh, my pen is running out. Horizontal intercept. Alrighty, so there are some key features. We're going to leave this situation and we are going to move on to another graph. So graphs are also useful for comparing 2 or more functions. This graph is about the population of Texas and California in the years 1900 all the way to 2010. C is our California. That makes sense, right? The output is the population. The input is our year. We can call it X. So C of X gives us our output, population. And X is our input, which is the year. T of X would be the population, which is our output, given the year that we're looking at, which would be our input. Okay, so let's look at some different things that we can tell about this graph. In the early 1900s, California had a smaller population than Texas. So let's check that out. Notice that Texas is this dotted line and California is the solid line. So down here in 1900, Texas, the dotted line, is above California, which is the solid line. So we can tell that that is a true statement just by looking at the graph. The Texas line is above the California line. Therefore, the population has to be more. All right, how can we convey this with function notation? Well, C is the population of California. When I input 1900, then C of 1900, the population in the year 1900, is less than the population of Texas in the year 1900. All right, so that would be a way to say this exact same thing in function notation. Let's look at the next one. Around 1935, the 2 states had the same population of about 5 million. Okay, so let's check that out. 1935, we look at the graphs, and they are exactly the same. It's where the graphs cross. So that's how we can tell that their populations are the same in that year, is because that's where they cross. So the graphs intersect at about 1935 and 5. How can we say that with function notation? Well, we can say the population of California in 1935 is 5. And the population of Texas in 1935 is 5. Since they're both 5, we could set them equal to each other and just say that the population of California in 1935 is the same or equal to the population of Texas in 1935. Alrighty. After 1935, California has had more people than Texas. Let's look. Yeah, they switch, right? Now Texas is below California. So California's population has increased faster than the population of Texas. Well, how can we show that using interval notation? Okay, so we have to put some constraints on x. So since it happens for any year that's bigger than 1935, we have to say that our years, which is our x, have to be greater than 1935. Okay, so given that the values of x are greater than 1935, then the population of California is going to be greater than the population of Texas. All right, for any year bigger than 1935. Both populations have increased over time with no periods of decline. Okay, so how can we tell that that's true? If the population was declining, wouldn't that graph go down? Yeah, it would. It would start to come down. The population in millions would start to decrease. But that doesn't happen for California, and that doesn't happen in Texas. So we could say that both graphs slant upward from left to right. Alrighty, that's how we can tell that the populations have increased over time with no decline. There's really not an easy way to say that using function notation. So we're going to skip that one, and we're going to skip the next one too. We're just going to talk about this. From 1900 to 2010, flip this down so you can still see the graph. From 1900 to 2010, the population of California has risen faster than that of Texas. California had a greater average rate of change. Okay, so how can we see that? You probably just saw the answer. If we were to connect the starting point and the ending point for California, I'm going to do that here. My red pen. Hopefully I did a good job. And then we were to connect the line, the starting point and the ending point for Texas. I guess I should have reversed that. Texas should have been red. Oh well. Too late now. All right, let's compare these. I just reversed it. This is Texas. This is California. Which line is steeper? California or Texas? Well, California is steeper than Texas. Texas is a little less steep. So then we know that overall, the average rate of change of California is bigger than the average rate of change for population growth in Texas. Alrighty, so comparing the slope, looking at the average rate of change can help us determine that. And visually, you look at the steepness of the lines. Those two things correspond. Okay, that's it. You're good. Go do your assignment in Delta Math. Have a great day.